have the word embeddings there.
Yeah.
And so the word embeddings, well, I don't know if that is well separated or not, it seems a bit convoluted. But what they show is that all the words that have similar embedding, they correspond to similar labels. So you are getting some sort of proper embedding, even if it's a proxy of a classification problem.
But it may not be embedding like a word to word. You may not be able to do arithmetics.
Yeah,
but they would be similar.
They find it closest. So those are the top 10. So second layer word embeddings. So just before the softmax, and then they take the top words for each class. So I mean, it seems like they are close.
Yeah, they are close, but can you do arithmetics? You know, like
okay.
They won't be related like you have in word to word.
So maybe not.
Yeah,
King and Queen melody.
But the advantage is here that they don't use any pre-trained word embeddings. So other methods require word embeddings to be trained previously. And here they don't do it, and then they still outperform the classifications. That's nice.
How fast is it to train?
You didn't mention the speed of training. I didn't see it.
No.
I don't know. I don't think I mentioned the speed. But it can't be too fast because the documents are pretty small. The documents they use are quite small. If you look here, they are in citation network records, you will see millions or hundreds of millions you will see. So they have only thousands.
Do you think we can use lots of documents? This, because you know, like the matrix will be larger and larger, and maybe at some point.
Yes, GCNs were used with much larger nodes, much larger number of nodes. It works usually because the matrix is very sparse, and then you can do clever things with that. But they didn't do it here.
Yeah, I think your main constraint here, memory-wise, is actually the embedding layer, so the weights, because the input matrix is a diagonal matrix. It's a one, so it's not going
very
to
sparse too.
You mean the X or the
so X is a diagonal matrix, so that is not going to take a lot of space.
Yeah.
But if you want large embeddings, which traditionally would give better semantic representations, then that is going to be very heavy. And then if you want to stack up layers, then that is multiplied more and more. No?
But then you can, no, you can't. Maybe one matrix, but not.
No, not with the non-linearity.
Sorry, someone asked this already. How do they pick the original number of classes?
But it comes with data set. Each data set comes with these classes. They didn't pick it. Cool? Done?
No, very simple question, I think. Where the convolution comes into place?
Well, if you look, then you put another element on top of this. Let me show it. It's a recursion, no? Well, that's the convolution, right? Because this is just one in there.
That's not a convolution.
The convolution is this. Here is the convolution. AX is the convolution.
But it depends
It's,
how this matrix looks like.
No, so it's if you take a look at the previous paper, they explain this. So this is so the convolution that they're doing is a moving average convolution, and what they show is that since this is an adjacency matrix and that is the degree matrix and so on, they can formulate the whole thing as a matrix multiplication. So this is doing the equivalent of a convolution.
So this looks like this. That would be a one matrix.
Yeah. So then they do d minus 1 a d d minus 1 half a d 1 half.
That's a big word for convolution.
But
Yes.
the convolution problem is not trained, right? It's essentially given by the problem.
This is fixed.
Yeah.
So this is the train of one.
The convolution is basically just take all of the neighbors of a vector and average its the neighbors of
Yes.
it. Yes. According to the weights on the graph.
Yeah.
Yeah, but I was wondering where it was happening, but that is.
Yes. So this is averaging. For that, it depends on the window size that you take. But for this one, it's averaging the self loop, TF-IDF, PMI, TF-IDF, and then you get one entry of that matrix, right? That multiplication, then you get that one with that one, the subgroup that one.
But it's not just averaging, it also well, averages with the weights on the edges.
It's based on the weight, right?
Yeah.
That's the convolution.
In graph convolutional networks, there is no trainable convolution term. Does it help?
Oh, is it?
Huh?
Oh, right. You're kidding, right? No.
No.
No, the convolution is AX, it's
Convolution-
defined always.
So you don't learn the weight.
So there's no
So it's not like a sliding
exactly.
window.
The kernel is fixed because it's defined by the connectivity, by the adjacency matrix.
Interesting.
You see, so it's more like a multilayer perceptron. So you have the convolution process associated with
It's
the
not local,
multiplication.
it's-
But multiplying by W, you see, is what gives you the traditional dense formulation.
But surely
Basically,
you
your graph structure gives you the convolution.
The graph structure gives you the convolution,
It comes with the graph structure.
but the convolution itself is not trainable.
but surely you can parameterize A, right? And then you can train for these parameters set.
Well, when A is already defined by the connectivity of the words.
Yeah, but the TF, for example, you could imagine scaling how important TF-IDF is, right? So it might be a very useful feature, it might be not a useful feature. And if you have parameterized that in the connection and have that trainable, it might tell you actually no, TF-IDF might be bad.
And that could be the content of your next paper.
You can add an attention mechanism on top of that.
Exactly,
And then
yeah.
you get trainable convolution as well. But I think that what they've shown is that they already get pretty good results from the graph connectivity.
Should we do the attention on the GCN's paper next time?
Yeah, there's a paper with attention on top of GCN.
Oh, there we go.
Anyone want
Sorry.
to you want to present it?
Too
or-
late.
No.
No. Anyone else
Boy.
wants to present it? No.
Okay.
We'll figure it out. We will find someone.
Well, thank you, Vahan.
Yeah.